is given by Bill Skamarock, and he talks about finite volume transport schemes for Voronoi meshes.
When I first started building models, I relied on others and what was in the literature to find transport schemes, and I used in them. And then with the Voronoi meshes, I started getting into this game myself. And what's striking is that for such a simple darn equation, there are thousands and thousands of microphone, sure. There are literally thousands of papers in the literature with methods to solve this equation. Here we go. Okay. So, and what I want to just talk about briefly today is some of the methods we've been using on the unstructured Voronoi meshes, because given that they're unstructured, a lot of the approaches that have been developed for structured meshes, essentially rectangular meshes, logically rectangular meshes, don't directly apply here, so you have to do something else. And at least I would say through the early part of the last decade, the schemes that existed that I was able to come across were quite low order, and the accuracy was not up to the standards of the state of the art, I'd say, on structured meshes. So I just want to talk a little bit about what we're doing here. So essentially, and I'm not going to talk about how we deal with a full solver. So I'm going to assume here that the mass flux, both the velocity and the density, if you will, are given, that they come from the dynamic solver, and that we know how this equation is updated. And the question is how to update this equation such that you maintain, if you so desire, the conservation properties, exact conservation with local and global, and consistency with this. That the question is how to do that. And what I'm going to show you are a couple formulations we've worked with on the Voronoi meshes that do accomplish that have varying degrees of accuracy. And essentially, these formulations come from thinking about the problem in effectively one of two ways. And of course, we're solving the same equation, so I'd say this is just a question of how you think about them. The first is that in our finite volume formulation, you can directly say, well, let's just integrate over space and time over our volume, boom, and use the regular transformation to get it as essentially an integral of fluxes over the surface here, and directly arrive at this equation here for the transport equation, which is just shifting the entire problem into determining the mass flux through the control volume surface over time in this manner here. So essentially we have to come up with some approximation of the space-time integral of the flux through the cell surface. Now, that's one way to look at it, and there have been a number of schemes that have been derived directly thinking in that mode. But there's a second approach which is just slightly different, I'd say. And that's, well, let's just integrate over the volume to transform our PD into an ODE. So you integrate over the volume, apply your standard trick here to deal with the fluxes. And so now we have an ODE here where we're just looking at the instantaneous fluxes through the control volume face, and we're going to use some ODE integrator, Runge cutter or something, to deal with the time integration of this ODE now. And I've been working on schemes that kind of take both approaches, and I want to show you some of those results today and what we've uncovered in trying to develop them. For those of you who are at PDs on the sphere, the global model that we're running both in the ocean and the atmosphere, MPAS, which uses Trisk, essentially we're using an approach which uses a Runge cutter time integration, so we have an approximation to this instantaneous flux through the control volume surface, and that's what I'm going to describe next. So I'm going to, even though I've listed these 1 and 2, I'm going to explain number 2 first in terms of what we do in MPAS, because it is what we are currently running, and then look at some other options. So in terms of MPAS, we've got essentially a kind of Runge cutter scheme. This is actually a third order accurate, this Runge cutter scheme for linear problems. It's only second order accurate for nonlinear problems. It has a nice property in that you're always starting from time t. It turns out time splitting to do something else for the acoustic modes is relatively simple with this form of the Runge cutter, and that's why we use it. So essentially, we're going to apply that to this equation here, where now we're just looking at these as instantaneous fluxes through the control volume surface as denoted here. So we've got to come up with some approximation here. As I mentioned earlier, our mass fluxes come from our dynamic solver, so we're going to assume we have those. We have the density, we have the velocities, so we know what that part of the problem is. So it really comes down to how do we specify the mixing ratios at the control volume faces that we plug into this formula for our time integration of the transport scheme. So in the literature, most of the models that run icosahedral grids, which of course the Voronoi mesh is, at least for the uniform resolution, or it can be configured that way on icosahedral meshes. The flux divergence term here, which is given here, which is essentially just thinking about it 1D, on the icosahedral meshes, essentially the value at the cell face was just taken at the values at the two cell centers that shared that face, essentially a second order flux. This turns out to be, while it's second order accurate, the solutions are rather poor. So we wanted to improve on that. In our other regular mesh, our Cartesian logically rectangular meshes, we used essentially higher order schemes, and this is, for example, those of you familiar with the regional model WRF, we use this. We essentially don't use a second order scheme, we use a higher order version of that. And one of those higher order flux computations comes back from Van Leer, and we picked it up from Hunsdorfer et al. It's a little harder to find here. This is a tome of a paper here. So we actually pulled it from here. But essentially, you can see the second order approximation of the mixing ratio to the cell face has been augmented by this term here. And when you add this term here, this is a correction that now gives you a fourth order flux divergence if you look at the 1D problem by adding this term here, where this is just the 1 minus 2, 1 operator here. And Hunsdorfer also pointed out that, okay, this gets you fourth order. You can develop a third order scheme by effectively upwinding this correction, if you want to think of it that way. And this adds a dissipation to the scheme. If you do the algebra here and expand this out, what you find is this looks like the fourth order scheme with a fourth order hyperviscosity term with a diffusion coefficient that's essentially this times delta T. That's what you come up with. A Courant number times, effectively a Courant number times a fourth order hyperviscosity. So we've been using this on our rectangular meshes fine. Of course, a problem on our Voronoi meshes is that we no longer have a universal coordinate, a smooth universal coordinate in which we can apply these operators. So we're kind of stuck, and we have to do something else to figure out how to build in this correction if we want to use this formalism here. And we have. And what we've done is essentially we just recognize that, of course, this is effectively just an approximation to the second derivative here. And we can recast the equation on the last slide here, our correction term, with just substituting this into here. And then the question is finding these second derivatives at the cell centers, because that's where the terms were evaluated in the operators on the last side. So that's what we're looking at here. And on the Voronoi meshes, we've been using essentially least squares fit polynomials to the cell centers for a number of our transport schemes, and we can use that polynomial to get an estimate of the second derivative, normal to the cell face, at the cell centers here. And indeed, that's what we do. So we use our polynomial fits, least squares polynomial fits, compute the second derivatives for that polynomial at the cell faces, and use those in these formulas here. On the perfect hexagons, it exactly collapses to, oops, let me go back to the last one. It exactly collapses to this here on the perfect hexagons, because on a perfect hexagonal mesh, you do have a universal coordinate. All the coordinate lines are straight, so you do recover this in the limit of the perfect mesh. But for the non-smooth mesh, we use that least squares polynomial fit. So it also tells you to compute a flux at a face here, consider this face E1, essentially our stencil uses all the points, all these points that you see here, all these cell-centered values to compute that flux. So it has a fairly wide stencil. But I think to get to these higher order schemes, you have to bite the bullet and realize you have to reach out for more information. So how does that perform? Well, here's an example from one of the test cases that Peter Laritzen talked about back at the PD's meeting. We have a whole suite of about 5 or 6 test cases with some variants of it. And this is essentially a Gaussian hill, so we have a smooth function which is continuous. So we can compute convergence rates, and you see that based on this result here, this is the number of grid cells here. This is, I'm plotting both the L1, L2, and L infinity here. And this is the -3, and that's the -2. So you see, we're seeing third-order convergence, and that third-order convergence is essentially tied to the use of the third-order Runge-Kutta scheme. That's why you get third order. So we're seeing that, and of course, when we turn on a limiter, and we have effectively an FCT limiter that we can limit the fluxes by, we no longer exactly converge at third order, but we maintain our accuracy fairly well. It's only something less than third order. And of course, the L infinity error is the one that gets hit the hardest there. So we're fairly happy with this. This was a major step forward, and if I compared it to second, if I even showed you the second order scheme, the errors would all be up here. It would look awful. So this was, we felt, a significant step forward for us in our developments in MPAS. One of the nice benefits of that is that what we found out was that just improving the transport of the scalars, and the place this shows up in the dynamic solver is the transport of, in our hydrostatic and non-hydrostatic models, the transport of the potential temperature. We saw a significant drop in errors in our solutions for some of the dry, very simple test problems. And this one here is from the Jablonowski and Williamson unstable baroclinic wave. So we're looking here in the northern hemisphere. The wave is essentially zonally symmetric at start. You put a perturbation on it that they give you, and after 9 days you get the lows and the highs and the wrap-ups of this is the temperature down at lower levels, cold fronts, warm fronts, seclusion region. This is vorticity down here. You get this structure, and in their paper they compared a bunch of models on this, and essentially the outlier, the poorly performing model, was a GME model, and this is on an icosahedral mesh. Of course, this problem with no zonal asymmetry there, it's zonally uniform except for the perturbation. It's built for a lat-long mesh model, so it's probably not a surprise that the GME model was somewhat of an outlier. And this is the phase error associated with this solution as a function of time. And how this phase error is computed is they just shift a very high resolution, what they considered a converged solution, and the phase shift to minimize the L2 error is what they define as the phase error. So that's what you're looking at here. And so this is the GME model, which is essentially a hydrostatic model. It's on an A grid. It's unstaggered on the icosahedral mesh. This is what we got with MPAS and also with ICON, which is a very similar model. It's being developed in Germany. Also on the hexagons, and Alma Gossman worked with me on this. And you can see we're seeing very similar errors, but shifted down, and we speculate that this is the difference between the A grid and the C grid here, but that's pure speculation at this point. And then finally, and that's with the second order operator. When we go to the third order operator that we're using in MPAS, and she also coded up an ICON, we see that the errors are then lowered down to a much lower level. And this is in the vicinity of what the other models in this study were producing. So we feel that just by improving the accuracy of the transport of the potential temperature in this case, we're seeing a marked improvement in our solutions. So one piece of our solver. And to just go a little bit further, one might think about this in terms of thinking about this, and that here we have a C-grid discretization. So we have a fairly accurate representation of the pressure gradient and divergence terms, and that now we have accuracy in our transport which more or less matches this. That clearly the error in the transport was dominating the error here, and by increasing the accuracy of the transport scheme, we're able to increase the overall accuracy of the solution. Okay, so there are other approaches, as I mentioned, that have been developed that I've been working on that are based upon stuff that the other people have done in the past, essentially the early part of the last decade. So you can go back and say, well, let's integrate over space and time and just try to deal with this in one shot, integrating the space-time integral of the flux through the surface. And a number of people have done that in various ways. There are two main kind of approaches that there are a number of papers on. And let me start with this one first, the one on the right. This is something that Todd Ringler over here and Bill Lipscomb worked on back in the early part of the last decade, where they said, okay, we're going to define our velocities, the full velocities on the cell vertices, and then we're going to go back in time and find out the area swept out by the flux coming through this face, and we're going to integrate this over the various cells that this flux comes from, and we're going to produce reconstructions for these cells and use those reconstructions wherever part of this area is in the particular cell. As you might guess, that can get very interesting because if these velocities, for example, they can be such that you get very interesting distributions of where that flux has originated from. So this is not an easy scheme to code, and the logic is kind of can be kind of difficult. And they essentially use first-order reconstructions. They use linear reconstructions when they did this. And I'm not going to show results directly from this. A couple years later, Hiro Miura came along and said, well, geez, this is more complex than perhaps one wishes. Let's just make an approximation. We'll define a single velocity at the center of the cell face, assume that it's constant along the cell face, and just have a simpler area to integrate over. And he even went further and said that, for example, if this velocity were pointing down further and this area that you would integrate the flux through passed outside of this upwind cell, he would just use this cell for that integral. He'd use the reconstruction for this cell as it even out here. So he made quite a few simplifications to that. And the bottom line was that the results you produced with this were roughly equivalent to the results you produced with this scheme. That the accuracy was not any different using the linear reconstructions in these cells. So we looked at this, and the accuracy wasn't fantastic in the grand scheme of things. So a number of us were thinking, well, let's increase the order of the reconstruction. So instead of a linear reconstruction, let's use a quadratic or even a quartic reconstruction. And I was working with a undergraduate student who essentially cranked through this formulation and showed that this very much increased the accuracy by using a higher order reconstruction using Miura's approach, the one where you just looked at a rectangular region, a simple rectangular region, assuming a constant velocity on that cell face. By going to a quadratic reconstruction, that greatly improved the accuracy. After we did this work, we found out that John Thuburn and a graduate student of his, Lashley, had actually done it, and it's in a thesis, but it was never published. So we didn't discover that they had plowed most of the same ground, but we effectively redid their work and went a little further with some of the limiters and some of the tests and got some good results. And we were going to go forward with that and use this scheme to do that. So essentially now, for a second order reconstruction, all you need is the neighbors of the cell to compute the reconstruction that could be used to compute the flux value through the surface. If you want to go to higher order, to fourth order reconstruction, then you have to use the neighbors of the neighbors. So your stencil gets wider and wider. But the fourth order results also were also very nice. And here's an example of some results that we had. This is for a deformational flow test case. Essentially, this is the initial distribution. It gets stretched out one way as it's transported around, and it comes back to this shape at time t over 2, and then it gets stretched the other way, the second revolution it takes, and comes back to this solution at time t. And these are the results. The red lines are the scheme that I just mentioned, both the second and the fourth order reconstruction. So you can see the fourth order reconstruction is giving us some better results. But, and this is relative to normalized costs, you can see it's significantly more expensive at a given mesh resolution, and these resolutions are the same here. And I've also plotted on this scheme the results from the scheme we're using in MPass right now that's based on Runge-Kutta. This is the normalized cost. Schemes that are to the lower left are better, are less expensive for the error you get. And you can see that the schemes based on Runge-Kutta are showing very good accuracy relative to the second and fourth order reconstructions in this pure forward in time approach, and are showing and are much less expensive. This is the reason we went with we're going with this right now in MPAS, in that because of this effectively this result here. Now, the forward time schemes can be improved upon, and I've been working with Hiro Miura, the Miura of the simplification of that flux in the forward and time scheme, same gentleman, and he took his approach and said, well, look, when he looked at other schemes, for example, PPM, one of the aspects of PPM is that, at least in the early part of its, when you go through it and construct it, before you worry about limiters and stuff, effectively it tries to maintain a continuity across the cell interfaces. And when we do our polynomial fits, for example, for this cell, and then if we do it for this cell, we'd be taking these neighbors here, we don't do anything to try to maintain any kind of continuity or even near continuity across that interface. And Hiro said, well, if I actually do an interpolation to the cell vertices and then fit polynomials to the cell center and then the cell vertices, least squares fit polynomials, that should come much closer to maintaining that continuity across the cell interface. So what he did was he said, okay, I'm going to interpolate to the cell vertices using essentially a weighted sum of the three cells that share that vertex, and then the next set of cells out, these green ones and these blue ones here. So this is what I'm going to do. And essentially the weights of those, the weights he used on perfect hexagons was he used 3/2 of the green ones and minus 1/2 of the average of the blue ones. And you might ask, well, where the heck does these weights come from? And it turns out that this leads directly to a fourth order accurate gradient operator on perfect hexagons. It's not too hard to show and to demonstrate. Unfortunately, on the Voronoi mesh, it's on the unstructured Voronoi mesh where they're no longer perfect hexagons. It's not quite clear how to maintain this accuracy, and you'll see in a moment that perhaps we are losing it somewhat. But this is the weighting we use. So now we have our values at the cell vertices in the cell center, and we do some least squares fit to that. So as stated down here, we've got these values, cell center, cell vertices. The values at the vertices are the same for the cell reconstructions that share that vertex. So you can see where the continuity or more near continuity of the fits might take place. It's important in these formulations that you make sure that the polynomial that you fit has the property that when you integrate it over the cell, you get the cell averaged value back, that you conserve mass in your fit, if you will. And we do that through a kind of interesting way. We actually compute effectively a correction value and subtract it from the cell centers, but add it to the vertices, such that when you integrate, do the least squares fit, you get a polynomial that does satisfy a conservation in that manner. And that's what we did. And we've played around with this a little bit. This seems to be the best way to distribute this correction in the fit, but we have no beauty principle, I would say, that derives from. Okay, so here's again our Gaussian Hills test case from Peter's test suite, in which we can look at convergence rates. And here you can see the red is this new scheme, and this black is the scheme from what we're running in MPAS now, from the Runge-Kutta integration. You say, well, geez, this is great. It's giving me much more accuracy. But no, we're not seeing third order convergence. We're seeing something less, and particularly at higher densities here, mesh densities here, more like second order. But I would much rather have more accuracy up here, where we're marginally resolving the flow, than worrying about the ultimate convergence rate of the scheme. And perhaps we can improve upon that by doing a better fit to the cell vertices. So we looked at this, and this looks fabulous. We were very happy with that. And I'd also say right here is that the cost of these two schemes are almost the same. So this is also telling you that the fact that this is to the lower left of this curve, that it's much more efficient. So it looks great. Another thing that caught my eye is that when we looked at discontinuous distributions, and this is the slotted cylinder after being transported by solid body rotation about the sphere. This is the new scheme. This is the old scheme that is based on the second order reconstruction just using the cell centers. And you can see that it doesn't maintain the sharpness of the slotted cylinder nearly as well here. And these are on the same resolution meshes. This is below, the bottom line is meshes that are half the mesh density as the top one. And you can see that we're getting very similar solutions at half the mesh density for these discontinuities, the discontinuous functions that we're transporting around in terms of the sharpness of the interfaces. So we really like this. And just one more slide to point this out. This is a much more difficult flow. Here's two slotted cylinders, and they're transported around in this deformational flow. They get deformed out, and then they come back to form the cylinders again. This is the new scheme. This is the old scheme. You can see there's more dark red, which is the high value here as opposed to the low value. Life looks good. This is giving a much better result. And you can see also in the filaments at the intermediate time, at the middle time, we're really handling that stretching much better here than here. We're not wiping out so much of the filament here. So it looks really good. Of course, not everything works perfectly. And this is a slide which demonstrates that. In further testing, actually testing here, it turns out, because Hero was the one pushing this forward, I finally implemented it myself and ran it and reproduced all the results. You've seen all those great results. And then I tried it on a different test, which is one I often use, which is this Blasi and Duran deformational flow test case, where it deforms one way and then the other. And I was expecting that life would be good. Here's the result on a 60-kilometer, nominally 60-kilometer mesh, and you can see it's nice and smooth down here. This didn't come out quite as well. I'll show some of these on the next slide. But what's going on here is that there's some noise developing when the limiter is on. So the unlimited scheme looks great. When we turn the limiter on in this test problem, we're seeing some issues with the FCT limiter, this nonlinear limiter, used with this scheme here. And these are kind of hard to see. It's a little bit easier to see in this slide here. You can see this here. This should be effectively circular. But of course, on a coarser mesh, it's going to be something less than circular, but it should be smooth. And you can see this feature forming here. This is with the full FCT limiter. We go to higher resolution. This doesn't go away. So the scheme with the FCT limiter here is not converging. And that's a problem. If we just use effectively positive definite, we just use the lower bound with the FCT, you can see it's somewhat less. It's still not perfectly circular, and you can say, well, okay, this is coarse resolution. You go to higher resolution, you can see some noise showing up. So there's something going on with the FCT limiter that it's interacting with this scheme in a way that's producing this problematic behavior for this test problem. I haven't seen it in any other. The slotted cylinders, whether it's deformational flow or just straight solid body rotation, all the others, I haven't seen the problem. This one we do. So to summarize, we've got a number of schemes we're looking at, and we keep looking at higher order schemes to see if we can improve things. Although we're happy with what we have in terms of going to applications now, but of course we would like to improve things if we can. And these schemes do show significantly reduced errors relative to the first order reconstructions that characterize the schemes we started with. The Runge-Kutta scheme appears the most robust. We don't see the problems with the limiters in it. We have a new scheme, but we've found out that there's some issues with convergence when we use with these FCT type limiters. I should say that the FCT limiter is not the only one we've used. We've also used Thuburn's universal limiter. So there's a question of the interaction between the basic scheme and the limiters that are nonlinear, and what can we learn from that. So with that, I'll be happy to take a few questions. Thank you.
Other questions? Todd?
So do you think the non-convergence is Due to the approximation of the back trajectories, due to the limiter, or fundamentally due to an interaction between the two?
I think fundamentally it's an interaction between the two. Because I've tried different limiters. So the FCT limiter, John Thuburn's universal limiter, those limiters seem to have a problem. I would like to try something more along the lines of essentially somehow adjusting the polynomial fit, the nature of the reconstruction, as opposed to adjusting the fluxes after the fact.
Right, we might be able to adjust the approximation of the parallelogram just to test that.
Yes, we certainly could. Phil Colella made a comment during the PDs on the sphere meeting that these limiters here are happier when with low phase error schemes. And I think the way we're reconstructing our polynomial in this new scheme is such that the phase error may be the leading order error now, or it's more pronounced. Even though it's more accurate, it's a more pronounced piece. Again, this is still, I'm showing you where we are, pretty much, that we've got some work to do if we want to adopt this scheme, which is showing nice accuracy for a lot of problems, just some problematic behavior for one.
Joanna?
Could you please go back to the slide when you have a Voronoi mesh and those kind of triangular looking, when you have this one, yes. Is this always, if we look at the blue vertexes, would they always form a triangle or is it a polygon?
Yes, essentially, so here's the Voronoi mesh here, and the dual is composed purely of triangles.
Yes, but what I'm asking is, if you join the blue vertexes only, would you have a triangle?
Yes.
Always triangle, it's not kinked. The sides are not kinked.
Well, it all comes down to how you want to join the vertices, and I've joined them with straight lines, but the straight lines have no meaning here. I'm just noting that these are the values I'm using in this thing here.
There is a kind of story in my question, in a sense. As a comment, perhaps, is the fit which you are showing there looks a bit familiar if you consider finite elements, second-order finite elements, with the vertexes which are being placed both in the with the nodes which are being placed both in the nodes and on the sides, which we typically use for to fulfill Babushka-Brezig conditions. So this is what translates to staggered meshes in finite differences, because then we would place pressure in the blue and velocities both in the blue and green. Where I'm going with my comment, if you like, is that you could use the finite elements on this type of second-order triangles already provide you with the ready-made formal derivation of in whatever point you want to have inside. So you could use this straightforwardly for your weightings, and this is a particular instance when you have derived it probably in a different way, but if you wish to generalize it, you could use the shape functions from the higher order triangular element for this.
That's certainly something we should probably look at.
But only if it's a triangle.
And maybe we'll get better convergence, but that's one of the problems.
Yeah, I would like to add to that there was also kind of an idea. When you project, so did anybody ever think about projecting this kind of physical representation, especially when you have non-uniform meshes, to a perfect, locally to a perfect hexagonal mesh, which would be the same as projecting the blue triangle to the unit triangle.
Well, that's
and then you can retain all the, then you can do the stuff on the unit triangle and project back, and then you have all the corrections, the geometrical corrections included in that projection. And the projection is very easy, it's just an affine projection. So that might retain your order of accuracy.
again finite elements.
That's a very similar approach, right? Yeah.
Yeah, just a comment. But I think the green circles there, they do not always fit the edge. So I think
Right. That is correct.
so that's
So
a problem too.
that is a condition
yeah, and
for a formal.
so you would get a polygonal thing, like you don't get a perfect triangle in that sense.
Yes,
you will
but-
get like a
Yes, but then you may introduce also slight inaccuracies in
Yeah, but you see, there are only 7 degrees of freedom, so you can, in general case, have just second order reconstruction, so quadratic reconstruction, not better. That's it. So you cannot do anything against that mesh construction.
Well, what's interesting, the second order reconstruction, if you were just doing a second order interpolation, the weights here would be 4/3 and minus 1/3. So we tried that, and the solutions aren't as good. That these weights give you the fourth order,
Yes, but from
Great.
finite elements, you would
Hexagons,
have
but-
the weights
right.
on the position. So.
but it doesn't tell you how to do this for the general mesh. So we don't see the accuracy we'd like to see. But then again, we see higher accuracy at the marginal resolutions, and that's what I'm focused on. That is, in my view, one of the most important things. So I'm happy with second order convergence if I can get lower errors.
The mesh is
At the
most
margins.
regular.
Because at the high resolutions, things are well enough resolved that getting a little more accuracy is not the issue.
Peter?
Coming back to those FCT limiters, when you talk about FCT limiters, are you referring to the actual procedure that compares some kind of like a template, lower order scheme,
Yes.
or just slope limiters?
Yes, no, I'm talking about FCT. I'm talking about the renormalization you wrote in your paper. That's where I took it from originally. You're the one responsible for me using this, Peter.
No, I don't mind.
Yeah, I'm not.
But the thing is that then this may explain those strange behaviors in some cases, because the best design for the FCT procedure is that when they're all lower order and the higher order schemes, they have the same phase error. Doesn't matter whether it's large or small, but the same. Otherwise, you have a shift of the higher and lower order schemes, and the whole procedure works on bringing them together, and it's not effective. So some schemes don't like to be mixed. They, like say, leapfrogs with upwinding.
Well, this could be part of it, certainly.
Further questions? That seems not to be the case. Then let's thank Bill again